So first of all, thank you all. This is really exciting. This is probably one of the most well-attended PhD defense because we do have people popping on online. Got a big family. Most importantly, Nana, thank you for coming. So this is a bittersweet day. We're very excited that Kyla is graduating, going to be an engineer at Fuss O'Neill, but that means she's leaving us, which is, again, she's had a really huge impact since being at Northeastern, from the academic side to run club to GSE. You really had a huge impact professionally and personally. So a little bit, just because I feel like all advisors have to. So when I first met Kyla, so Kyla came from UConn and she came out of her bachelor's to do a direct PhD. And I just remember thinking, wow, she's really excited and she's really curious and she's up for an adventure. And I was like, this is fantastic. You know, that personality really has cultivated into this amazing program that has really helped shape a lot of science and helping policy, as you'll see, in North Carolina. So I'm really excited that you wanted to, let's just go. Like, let's do this. So every time I ask her, she's like, okay, we'll do this. Sure, I'll go follow this hurricane. Sure, let's go do that. So that has really helped. I think your experiences here have really been really impactful, especially to society. So I'll just close out just to say some of the accomplishments. Kyla is a Cochrane Fellow. She also just recently received a dissertation fellowship from Northeastern, which honors students who have really strong programs that they want to see them be able to really have a well-rounded program. So she's extended her position here for 2 extra months just to get these papers into publication. And again, help the state of North Carolina figure out what to do after hurricanes. And her work she's going to show today is being funded by NASA through 3 different programs: Water Resources, Global Precipitation Mission, and SWAT, as well as NSF through Strengthening American Infrastructure. So I'm really sad, but I'm really happy for you. So just a little bit of housekeeping before I turn over to Kyla. She's going to go for about 45 minutes. And then because we do have some health departments and friends online, we're going to do online questions first, and then we'll do audience. So with that, here we go.
So good morning, everyone. Thank you so much for coming. I'm Kyla, in case you don't know, and today I'm going to be talking to you guys about the work I've been doing over the past 3 years, exploring barriers to safe drinking water access from private wells to support environmental health. So before I get started, like Kelsey mentioned, this work was supported by so many different partners and collaborators, and so I just want to take a minute to say thank you to everybody. This list isn't exhaustive, but thank you. So a little bit of background: private wells provide drinking water to nearly 45 million Americans, including my entire hometown and my Nana, whose well is featured right here. And these systems are federally unregulated, and so well users are responsible for maintaining their own drinking water quality. Federal and local state recommendations suggest that well users should test their system for bacteria every year and for other inorganic contaminants every couple of years. But despite these recommendations, nearly half of well users in studies have said that they have not tested their system ever before. And this is problematic because well water quality is highly variable. So factors like system characteristics, disasters with floodwaters entering the systems, and underlying geology, so contaminants that are in the rock and aquifer, can all influence water quality. And without testing, these different conditions can go unknown. And so our team is funded by NASA to develop a well water surveillance and response system, working with the North Carolina Department of Health and Human Services to do 4 different tasks: enhance monitoring and sampling efforts, target response after disasters, target outreach and preparation of a hazard, and map contaminants over space and time. And so today I'm going to talk about my contributions to this really huge project. So the agenda, how it's going to break down. I'm going to talk first about chapter 1, which was my master's thesis, where we use different flood mapping tools to predict microbial contamination in private wells after Hurricane Florence. Then I'm going to talk a little bit about something that didn't become a core chapter, but was really pivotal to furthering this work, which was some of our real-time flood mapping efforts and sampling after Hurricane Debby. Then I'm going to go into our work on Hurricane Helene, which there were two main projects. First, how flooding, landslides, and on-site infrastructure damage contributed to contamination after the storm, and then estimating floodwater, groundwater connectivity. Finally, I'm going to take a step back and talk a little bit about routine testing conditions and the benefits of repeat well testing over time, using Virginia as an example. So with that, let's get into it. So this first chapter, like I said, is my master's thesis. The results are published in Environmental Science and Technology, and if you're interested, you could go take a read of the publication, but I'm just going to do a quick overview of our main findings. So the main question that we are trying to address here is how can flood mapping predictions be used to advise well water recovery efforts? So we used multiple different flood mapping methods. The first is a 100-year flood hazard area, which is derived using hydrologic and hydraulic models to estimate locations that have a 1% chance of flooding in any given year. And so this is a static boundary that exists across most of the country and is often used for flood insurance mapping. And after Hurricane Florence, this is what the 100-year flood boundary looked like in our study area. We also used a second method, which I'm going to talk about pretty extensively throughout this presentation, which is the height above nearest drainage hand-derived extent. This incorporates reach average relationships between water depth and river discharge. And if you're like, what does that mean? I'll break it down a little bit. This is more of Ed and Reza's wheelhouse, but I use these maps, so I'm going to do my best to explain them. If you have a point up on a hill and you're wondering, what is the flow rate required in that stream beneath so that those floodwaters overtop and reach that point on the hill? And what HAND does is uses stream flow gauges and predictive models to determine thresholds to see if stream flow reached the threshold so that that point floods. And so what you end up with is a map of locations that either flooded or didn't flood, and the flooded locations are represented in blue. And so this is storm specific. To validate these methods, we brought in some sampling data to understand where areas that were flooded also had microbial contamination in wells. And so we looked at two different types of bacteria. The first is total coliforms, which are found in soil and surface water. And these are more of an indicator bacteria. They are fecal and non-fecal. So it indicates there's bacteria, but not necessarily a health concern. E. coli, which is a type of total coliform, is a fecal contaminant found in the intestines of warm-blooded mammals, and it is a serious health risk. And so we used 3,000 tests from routine conditions from 2009 to 2017 in the study area to try to get an understanding of what routine water quality looked like, and then compared that to 754 tests that were collected by the health departments after Hurricane Florence, September to November 2018. And what we found was total coliform increased 1.2 times from routine conditions, and E. coli increased 7.6 times. So wells under routine conditions had 1.5% E. coli positivity, but after Florence, that shot up to about 11.2%. And while these were pretty substantial changes, it's important to note that there were no wells tested in both the routine and post-Florence data set. So this isn't a direct paired comparison. So when we compared our two flood boundaries, we found that the ability to detect E. coli positive samples varied. So the 100-year boundary, when we overlaid it with our tests, had 60% of all E. coli positive tests within that flooded area, while the hand boundary had 20% of E. coli tests within the boundary. So while these boundaries were able to detect areas that had elevated contamination, there was still high rates of contamination outside of the flood boundaries. And so none of these models were able to fully capture microbial contamination. And so our main takeaways were that 60% of E. coli positive wells overlapped with the 100-year flood boundary. So this is something that could be used by health departments to understand where they should be targeting their testing efforts. And we found that contamination was increased within flood boundaries. But the 100-year flood boundary is static, unlike the hand boundary, which is storm specific. We also lacked paired baseline data to quantify those changes more accurately. And we found high rates of contamination outside of flooded areas. And so this kind of identified two major needs that motivated some of our future work, which was the need for real-time accessible flood mapping tools and robust and reliable routine testing data. And when Hurricane Debby hit in August of 2024, we had an opportunity to start to explore those two needs. So here we enhanced sampling and monitoring efforts to develop real-time estimates of flooded areas. So building on the work after Hurricane Florence, two of our collaborators, Ed and Colin, took the hand boundary and optimized some of the parameters to calibrate it to that 100-year boundary so that we could have a storm-specific map that performed better. And so the question we are trying to answer here is, can we provide health departments with a near real-time flood map? And so using this Jupyter notebook, you can select the region that you're interested in looking at, enter the date range for the event, and out pops the flood boundary. It is far more complicated than that, but Reza makes it look easy. And so then we're able to use this flood boundary to estimate impacts. And so at the same time, I'd been planning a sampling campaign in Eastern North Carolina with 6 different local health departments. Shout out to all of them there. Hi, if you're online. And originally, we were planning to do this as a baseline testing campaign to understand what routine conditions looked like. But the timing of the unpredictable weather in North Carolina, like it does, made it so that Tropical Storm Debby made landfall about 5 days before we were about to sample. And so this kind of changed the way that we advertised the campaign. And we tried to get residents to understand what the risks of flooding might do to increase participation. And it worked. We provided 350 free well water kits to 6 different local health departments. Here are all of the kits that we packed up with instructions on how to sample, a survey that residents took, and then the 3 different bottles that tested for a bunch of different inorganic and microbial contaminants. In total, we got back 228 kits. So 68% of kits that we sent out were returned, which is a pretty high response rate considering we hadn't sampled in this area before. Notably, 34% of tests were positive for total coliform and 3% were positive for E. coli, which suggested pretty minimal impacts from routine conditions. And when we were talking to residents in North Carolina after the storm, they kind of agreed that the impact of Debby was minimal. So while this was a good outcome, we had a chance to do 3 important things. First, we empowered well users to make data-informed decisions by providing them with test results and an explanation of how they can reduce any potential contaminants in their system. Also, we established connections and engaged a cohort for future testing. So we have those 228 households information, and we're hoping to engage that cohort in the future for more testing. And finally, we were able to pilot test real-time flood maps. We developed a boundary, we had samples to compare them to, and we kind of knew how to do all of this in real time. So this set us up really nicely to be prepared when 1 month later, Hurricane Helene hit in Western North Carolina. And so here we provided real-time data for decision-making by health departments. For those of you who don't know, Hurricane Helene brought historic impacts to Western North Carolina in September of this past year. There was devastating ground disturbances and landslides that shifted the topography of the land, and there was high ravine flooding. This was particularly problematic from our perspective for well users because the density of private well usage in Western North Carolina is pretty high. So you can see these areas outlined in yellow, and then these clusters of dots indicate areas that are heavily reliant on private wells. So Western North Carolina is pretty rural, and therefore there was a lot of people relying on wells for their drinking water. And so in these past 2 projects I've discussed, I've talked about how health departments provided us with data, or we collaborated so that we could further our research goals. Hurricane Helene was a chance for us to take a step back and see what we could do to provide resources to the health departments. And so this is a timeline of some tools that we developed to try to guide recovery efforts in real time. So on Friday, the 27th, which is when the storm was making landfall, we had a meeting to discuss needs and develop a plan with the health departments. They said that they could potentially use some flood boundaries. And so we developed a hand boundary for the method by Monday, the 30th. Once we showed them that flood boundary, our conversations kind of increased and they started asking for more data layers. So can we see what schools were impacted? Can we see what businesses were impacted? And so we started to gather and compile a bunch of different data layers. And on Thursday, the 3rd, we sent out a draft of a product to local health departments for review. By Monday, the 7th, they provided feedback on how we could make the interface more user-friendly, some additional data products we could have. And by Monday, October 7th, we had launched a portal that had recovery data to be used by health departments. And so there was 3 kind of products that came out of this. The first is our data support system, which we launched. That incorporated real-time flood boundaries, rainfall data, potential hazards, impacted areas. But we also took some of this data and generated them into reports. And so we had county level reports and reports for the whole area that were used in real time for decision making to quickly say, this is how many wells we think were impacted by flood bounds. And then a couple of weeks later, as part of my Casey Donnelly externship, I went down to North Carolina and worked with a group of nonprofits, people from the National Groundwater Association and local health departments to design and build mock wellheads that were used as educational tools. So we brought these systems to local health departments so that they could show well users what their system should look like and how they could potentially disinfect it if they think they were impacted. And so all of these efforts led to our involvement with the development of a post-storm sampling protocol. Immediately, sampling wasn't on the forefront of people's minds because the impacts of Helene were so severe. But when it came time to do sampling, because we had had this relationship, we were included in these efforts. And so now I'm going to move into the second project, which was how flooding, landslides, and on-site infrastructure contributed to microbial contamination after Hurricane Helene. So when sampling began, this was a multi-agency sampling campaign that combined federal, state, and local efforts. So the Environmental Protection Agency had mobile labs that they set up. The state was running samples through the State Lab of Public Health, and 13 different health departments and 8 certified local labs came together to all collectively sample. So in total, 6,400 free well water testing kits were sent to local health departments. 2,700 well water tests were returned, and 1,600 disinfection kits were distributed. So disinfection is a really common treatment method to remove microbial contamination from wells. It's similar to shock chlorinating a pool. And so providing these kits to well users allowed them to try to mitigate some of the impacts of the storm with treatment. And so our objectives were to use this really rich database that was developed to first quantify the extent of impacts and response through testing and microbial water quality. Second, evaluate the variability of contamination across different risk factors, including flooding and landslides. And then finally, assess damage in the federal distribution of aid across impacted counties. And so some of the data sets that we incorporated here, first were those 2,700 well samples and estimated well use in the area, which we took from our decision support system. We also brought in data from the Federal Emergency Management Agency, or FEMA, on the number of systems and amount of money that was distributed at the county level for the repair of septic systems and wells. We brought back in our hand flood boundary to estimate the impacts of flooding, and we used United States Geological Survey data on ground point failures to estimate areas that were impacted by landslides. And so to estimate the predicted prevalence of E. coli in private wells, we use the logistic regression. And basically what I'm going to explain to you is that we used 18 predictors from 4 different groups, including physical risk from the storm, sampling behaviors, socioeconomic variables, and variables over space and time to estimate if an E. coli sample was negative, a 0, or a 1, positive. And so how we're going to interpret these results is using average marginal effects, which is reported as the predicted probability in change from observed probability. So if 8% of samples were E. coli positive, how does changing one of those predictors impact that outcome? Does it change it to 10%? Does it change it to 6%? That's the way we're going to interpret it. And so moving into results, total coliform and E. coli remained elevated for several weeks after the storm. So of the 2,700 samples returned, 2,300 unique households participated. So that indicates that 220 participants sampled more than one time during the study period. On average, we saw 324 samples per week, but you could see that that wasn't evenly distributed over time. And there was a 4 or 5 week period when the sampling protocol was in its main stages that the majority of samples were returned. We also found that total coliform and E. coli both remained elevated from routine conditions for multiple weeks. So on average, 38% of samples were total coliform positive and 9% were E. coli positive, which is comparable to what we saw after Florence when 38% were TC positive and 11% were E. coli positive. So this is 7.7 times higher than routine conditions. We found that disinfection use was limited but effective. So of those disinfection kits that were sent out, 576 samples came back with disinfection information included. 20% of those samples were disinfected and came from about 12 counties. What we saw was that of the samples that indicated they were not disinfected before the sample was taken, E. coli was 3 times higher than among the samples where disinfection was done before sampling. So disinfection reduced E. coli positivity by 3 times. We also saw that contamination results may have been a driver in prompting follow-up testing. So of those 220 testers that sampled more than one time, we found that between the time of their first sample and the time of their last sample, E. coli contamination was 2 times less. So there was something going on between the time of that first sample and the time of the last sample where participants made efforts to reduce contamination. Notably, there were 2 to 9 samples per participant that tested more than once, and on average, there was about 2 weeks between those samples. In total, 18 counties returned samples, but these were pretty highly concentrated among a few counties. So 60% of samples came from 2 counties, which is where the 2 EPA mobile labs were stationed, indicating that access to testing or visibility of testing may have increased participation in those areas. But overall, there were 8 counties that had more than 100 samples returned. And so for the rest of our analyses, I'm going to focus on those 8 counties. Among those 8 counties, about 3 to 9% of land area was flooded within each county, and each county experienced between 40 and 320 landslides. So there was pretty substantial impacts within these areas. And now looking at sampling within these estimated areas. So these gray bars represent the percent of samples that were within flood boundaries. And we found that across the 8 counties, sampling varied, as well as the presence of E. coli within those flood boundaries. So I'm going to compare E. coli positivity inside risk areas and outside risk areas. So inside risk areas are these dark colors here, and then outside the flooded boundaries are represented in the light blue here. What you would expect to see is that within flooded boundaries, E. coli positivity is higher than outside flood boundaries. And across the 8 counties, that is generally what we saw. But there were a couple examples where we saw unexpected results where E. coli positivity outside the flood boundaries was higher than within. And when we looked at disinfection rates, we found that among those 3 counties where E. coli positivity was higher outside the boundaries, 50% of all samples that were disinfected came from those 3 counties. So disinfection may have been a factor in why we were seeing lower E. coli positivity within flood boundaries. The other thing we noted was there was a substantial impact of landslides as well. So similarly, this is the percent of samples that were tested within 500 meters of a landslide. And the dark circles represent the percent of samples that were E. coli positive within those landslide impacted areas and outside. And so again, we see some trends that would be expected where E. coli positivity is higher within areas that were heavily impacted by landslides. And in particular here, I want to call out Ashe County, where when we looked at flooding alone, E. coli contamination was higher outside of the flood boundaries. But when we look at landslides, we see that the E. coli positivity was much higher in areas that were impacted by landslides, which might suggest that landslides were a bigger driver of contamination within that county. Now, each county had limited sampling within some of these flood boundaries, and so it was kind of difficult to determine statistical significance for some of these comparisons. But overall, we saw that time in disinfection drove E. coli positivity, not these risk factors. So 7.2% is the probability of testing E. coli positive if you disinfected your system, compared to the observed positivity rate of 8.5%. So disinfection alone reduced your probability of E. coli contamination by 1.2%. Also, for each week following the storm, the probability of testing E. coli positive was reduced by 4.2%. And this kind of makes sense because bacteria is alive and it has a lifespan. And so as time goes on, some of the bacteria that got into these systems is going to die off. So time and disinfection really mitigated these impacts. Damage was really severe following Hurricane Helene. And because sampling was limited in some of the most impacted areas, we think this might have reflected the amount of damage that happened in these areas. So many systems were completely overtopped, pulled out of where they were in the ground. Some were uncovered with land. So originally that whole part of that casing was underground or covered in sediment. So they were unusable after the storm. So looking at overall impacts, $3 million in aid was distributed from FEMA for on-site infrastructure replacements and repairs. So 1,900 systems were documented as either repaired or replaced across 40 counties, but 99% of that aid distribution was within our study area. And the amount awarded per county varied pretty substantially, from less than $10,000 to over $500,000 within a county. So some counties were much more heavily impacted than others. And that's reflected here, where 3 counties, Buncombe County, Yancey County, and Henderson County, accounted for 50% of all well-related damages. And so when we look at the relationship between damage and some of our environmental risk factors, we found that damage was more strongly related to landslides than flooding. So I'm going to show some maps here, and I just want to break down before I get into it. This x-axis here is the amount of damage money that was awarded, from less than $50,000 to more than $100,000. And this y-axis here is the percent of area that was flooded in a county. What we would expect to see is this dark brown color here, where there was a lot of damage distributed and high impacts. For flooding, we saw this a little bit, but you'll note that there's these eastern counties here that are blue, which is indicated as having a lot of flooded area, but not a lot of damage. And the reason for this is likely twofold. The first is that there wasn't very substantial differences between the amount of flooded area across counties. And also, this is just the amount of land area flooded, and it doesn't account for where people are living within the areas that flooded. So it's possible that the same amount of land flooded, but it impacted fewer people. When we look at landslides, though, these results line up a lot better. So you could see a lot of those dark brown colors in the middle there, which is where there were counties that had an increased number of landslides and more damage money awarded. So this indicates that those ground disturbances and those landslides contributed really heavily to the damage to wells and septic systems. And that was reflected in the amount of aid they got. We also found that damage was more strongly correlated with testing than contamination. So in counties that returned more samples, there was a stronger relationship between the number of wells that were replaced than looking at the rate of E. coli positivity against the number of wells replaced. And so what this likely suggests is some of these most impacted areas had good turnout for sampling, but the most severely damaged systems were unable to participate in sampling because their systems were out of use. So we're not seeing as high E. coli positivity because the most impacted samples didn't come in. And so the main takeaways were that time since the storm and disinfection were the two most important preventative measures for reducing E. coli contamination. Contamination was also driven by landslides more than flooding, which is contrary to what we've seen in coastal storms and indicates a really big difference between the way these systems operate in mountain areas. And finally, the most severely damaged areas were likely unable to participate in testing because their systems were out of use. And so that kind of leads us into our third project, which is estimating floodwater groundwater connectivity through private wells during Hurricane Helene. So looking at, even if your well wasn't specifically overtopped, could you see contamination rates outside of flood boundaries because the underlying aquifer is connected? And so our objectives here were to first identify changes in static water levels after Helene using monitoring well data, then compare wellhead coverings in their ability to protect systems from floodwater intrusion. So basically, when they're overtopped, can this cap prevent water from leaking into the well? And third, estimate the potential for contaminated floodwaters to enter the groundwater via overtopped wells. So again, we're incorporating our hand flooding boundary, but here we added factors to incorporate flood height and duration of flooding. So we set a minimum threshold for an area to pop up as blue there if there was 40 centimeters of standing water on the ground, the amount that would typically cause a well to overtop. And we looked at this over 1 hour increments over the study period so that we could see a time series of the wells that we thought were likely overtopped. And this is how that looked. So areas in that dark blue there were flooded for longer than wells that are maybe on that light blue area, or wells that are in the white that were not overtopped at all during the study period. And so I'm going to be talking about static water levels, and what I mean by that is here. In the well, there's a static air column. It's not entirely filled with water, and that depth from the ground surface to the water level where groundwater is sitting is what we're going to refer to as the static water level. And when increased water gets into the aquifer, that static water level might rise, and in drought periods, it might fall. And so when we looked at monitoring well data, we brought in 24 different wells across the impacted counties and looked at the static water levels over time in 2024 when Helene hit, and then from 2000 to 2023 to understand baseline trends. We grouped each of these by flood status by laying them over that hand boundary, and we normalized changes in baseline. So starting at September 14th, which is when we looked at things, that is considered 0, and then changes from baseline are compared to 0. And so what we saw was across all 24 systems, there was rapid changes in water levels after Helene. So this is September to December, and you could see for the majority of these systems, those dark lines increased pretty substantially from the dashed line underneath during the period when Helene hit. And when we brought these estimates together and combined all flooded wells with all non-flooded wells, we saw that on average, flooded systems saw more significant changes in water levels than non-flooded systems. So the maximum change from baseline here increased for non-flooded wells, but it increased by 21.6% more in flooded systems. And so what this indicates to us is that there was impacts among flooded systems that non-flooded systems did not experience. And so looking into maybe how some of that happened, if there was water that was getting into the systems from overtopped wells, we changed our focus to looking at this well cap. So these are designed to prevent debris, water, and other contaminants from getting into the system. And there's 4 different types of wellhead coverings that we looked at that would likely be within Western North Carolina. And so from expert opinion, we looked at the standard well cap. So these are loose fitting caps that sit on top of the well casing. And the sanitary configuration is watertight with those bolts sealed around it. We estimated that only about 2% of well users in North Carolina use these systems because they require a different construction than the bottom 2 configurations. The bottom 2 is a well seal and a sanitary well seal. This rubber piece that goes around fits inside of the well casing, and so it sits flat on top of it. And it can be configured with a vent, which removes that open hole space and creates just slotted areas for water to get in. And we estimated that 39% had a well seal and 59% had the well seal with the sanitary configuration. So I'm going to compare each of these caps or each of these coverings as standard and then sanitary. To estimate these, we did a lab experiment. And so we built a well rig in the basement of Snell. And what we basically did was retrofit a wellhead within a larger bucket, filled that water up, and we had a water sensor and an air sensor outside the system. We monitored the speed at which water came out through the bottom of that bucket using the sensors and estimated the change in height over time. We used that times the area of the bucket to develop Q, which is the flow rate of water coming out the bottom of the bucket. And so when we built it up, this is what it looked like. We drilled a PVC pipe into the bottom of a trash can to make it watertight and retrofit it with a gasket here so that we could pull the gasket and allow water to start flowing, which is when the sensors started to monitor those changes in height. And what we found was the duration it took for these to drain varied substantially across well caps. So from the well cap to the sanitary cap, there was a difference in taking about 10 minutes to drain to taking nearly 24 hours to drain. So the sanitary configuration really protected a lot of water from getting into the system. Comparing the well seal to the sanitary seal with the vent, we saw similar trends, taking less than an hour to drain and then up to 6 hours to drain when we added that sanitary configuration. And so something else that we found from these results was that these flow rates varied substantially depending on the height of water above. So we started with about 12 inches of water above the well covering. And as the water drained, the rate at which water came out through the bucket slowed down. And this makes sense when you think about the pressure that that system is under. And so we fit models for each of the caps. And then we focused in on 5 centimeters above the wellhead, which is where that 40 centimeters of flooding threshold likely was occurring. And so when we looked at that, we found that the difference in flow rates, again, varied really substantially between the standard and the sanitary configurations. So for the well cap, it was 650 times less. And for the seal, it was 17.4 times less when you went from the standard to the sanitary configuration. We brought in our duration using hand, and from the 2,600 tested wells after Hurricane Helene, we estimated that 117 of those were overtopped for at least 1 hour. When we brought in the total well data from our decision support system, we estimated that about 13,800 total wells were overtopped. And so using the duration of flooding, we're able to estimate the total volume that might have gotten in, assuming different wellhead coverings. So we're taking that lab experiment now and scaling up pretty majorly. So first, just looking at the 117 overtopped wells, that's about 5% of the total wells that were tested were overtopped. And on average, they were overtopped for 19 hours, but this varied from just 1 hour to systems that were underwater for over 7 days. And here we're looking at, over time, the amount of area that we estimated as flooded. So this is the results of laying those hand boundaries at 1 hour on top of each other and calculating the total area. And we saw that the amount of area flooded peaked at the same time that precipitation peaked. And so this is using satellite data to estimate precipitation intensity at centimeters per hour. And you could see that the two periods in which rainfall peaked coincided with when flooding started and when flooding peaked. And when we lay over those 117 wells that were overtopped, we see the same trend. All three, peak inundation, the number of impacted wells, and peak precipitation all overlapped, indicating that flooding was driven by precipitation and led to impacted wells. To do this scale up, we had to make a bunch of major assumptions. And so we kind of tried to bookend it with two different flow assumptions. So the first is assuming that that air column in the well can fill up with water, but then after that, no water is coming from the bottom of the well into the larger aquifer. So that's the minimum estimate. And using standard configurations of wells in the area, we estimated that on average, there's about 180 liters of static airspace that can be filled by floodwaters. We also developed a maximum estimate, which is assuming that 100% of the water that goes into the well goes out into the aquifer. And that is definitely an overestimate, but it gives us an idea of how much water could have potentially gotten into these systems. And so when we looked at the time it may have taken for that 180 liter well column to fill up with water, we found for the standard well cap, it would take about 6 minutes. And for the well seal, it would take about 24 minutes. Looking at the sanitary configurations, those times increase really substantially to 43 hours and 6.5 hours. So adding those sanitary configurations really limit the amount of water that could get into systems in a short period of time. So here we scaled up to those maximum estimates to see how different coverings impacted total estimates. So what I really want to point out here is the difference between the seal and the sanitary configuration resulted in 5.5 times less total volume getting into the system, and going from well caps to sanitary caps resulted in 37 times less water getting into the system. But overall, using those estimated distributions of coverings from our experts, from 117 wells alone, over 1 million liters of water could have gotten into the underlying system. And when we scale this up to all estimated overtopped wells, those 13,800 wells could have added 120 million liters to the groundwater system. So even if your well wasn't directly flooded, there's 120 million liters of floodwater that may have gotten into the aquifer you're using to pump. And to understand what that really looks like, that's enough water to fill 48 Olympic-sized swimming pools. So The main takeaways here were that flooded monitoring wells had more substantial changes in static water levels than non-flooded. Infrastructure choices significantly impact the amount of water that could get into these systems, and a lot of water likely entered the aquifer via overtopped wells. And this is an area that I think we really need to consider more because the connectivity of these systems is not often understood. And so I'm going to take a sip of water. Okay. Our last chapter, we're going to zoom out from all of that hurricane talk and focus in a little bit more on the issue that I've talked about kind of throughout this, which is that we don't have good routine testing data to compare to flooded impacts. So here we're going to look at Virginia as a case study and look at the benefits of continually testing over time. Routine testing data is essential to contextualize changes in water quality over space and time. And so for this project, we worked with the Virginia Household Water Quality Program, VHAQWPA. I'm going to say that a lot. And you're going to be like, what? VHAQWPA is what we call it. And over an 11-year period, VHAQWPA analyzed 20,433 private well tests from about 16,000 unique participants. And so when we're talking populations of interest, I'm going to be talking about those who tested their system one time throughout the 11-year period, which is about 14,000 participants. But I'm really going to focus in on these 2,000 participants that came back for testing more than once. And so our objectives here were to characterize testing behaviors and water quality across Virginia, then identify the impacts of repeat testing and use of treatment on water quality outcomes, and then quantify the factors influencing participation in repeat testing. And so just to talk a little bit about the structure of VHAQWPA, they operate through 107 different extension offices across the state, and they hold drinking water clinics that VHAQWPA hosts, and then extension offices decide if they're going to participate in those clinics. And so over the 11-year period, 237 clinics were hosted at 97 extension offices, so about 94% participated. On average, there was 22 clinics per year, and 56 offices participated. We also looked at their staffing, and so there was about 600 staff across all 107 offices, 75% of which were full-time. And on average, there was 4 staff per extension office, although this ranged pretty widely from 1 to 20. When we look at water quality, I've mentioned before that wells are federally unregulated. And so we're going to use recommendations from the Safe Drinking Water Act, which are used for municipal drinking water systems, but they set health-based standards and nuisance-based standards. And we're going to use those to quantify water quality in private wells. And so there's a whole bunch of contaminants, and we're going to focus in on those health-based and those nuisance-based, which are each of these ones added together. I'm also going to talk about drive times, hotspots, and logistic regressions, and just to establish the methods that we used here to estimate how long it took to drive for each participant from their home to a testing location. We used a road network analysis and the closest facility network tool in ArcGIS. We minimized travel costs, accounted for road hierarchy, why you would choose this road over that road, travel time during business hours, and speed limits. And we estimated for each of those dots there how long it would take at a minimum to reach one of the yellow dots, which is one of the extension offices. So how long were people driving to access testing? The second thing we did was spatial hotspots of testing. So using those dots, locations where tests were taken from, we counted a hotspot grid. So using 10 by 10 kilometer square cells, we counted the number of testing locations in each area and determined if it was more tests than we would expect to see or less tests. more tests were considered hotspots, less tests cold spots. We did a logistic regression again, and this time our Y was whether a participant repeat tested. 0 is no, 1 is yes. So we had about 2,000 yeses. We had predictors across 4 different categories. And again, we're interpreting the results as average marginal effects. So change in probability from what we saw to what we predict. Overall, we found that testing increased substantially over time. So Fahalkupa had pretty substantial growth across the 11-year period, but contamination remained pretty constant. So health-based exceedances and nuisance-based exceedances didn't vary much over time. 12% of participants were repeat testers. And so on average, those 1,800 participants returned 2 to 11 samples, and there was about a year and a half between participation in clinics. And so what we saw here is while the total number of repeat testers increased over time, the number of new repeat testers varied more substantially. And so this indicates that people who start repeat testing continue engaging in testing, but the rate at which residents are deciding to repeat test varies from year to year. Looking at differences in water quality and treatment between those who tested once and those who tested more times, we found that one-time testers had similar initial water quality. So looking at those health-based exceedances, there was not a significant difference from those who tested once or those who tested more than once. However, when we look at those using health-based treatments, we saw that initially repeat testers were using treatment systems more frequently than those who only tested one time. And so this indicates that maybe those repeat testers were more engaged with their water quality stewardship to begin with. And so they knew how to treat their system and were more interested in seeing what their water quality results looked like. When we looked at repeat testing over time, from the first repeat test to the last repeat test, we found repeat testing was associated with decreased contamination and increased use of treatment over time. So health-based exceedances significantly decreased, lead decreased by 2.2 times, and total coliform also decreased significantly. We also found that use of treatment increased by 1.3 times. And so repeat testing between the first test and the most recent test had quantifiable benefits in improving water quality and use of treatment. We found that testing was related to the amount of clinic opportunities. So looking at this map here, 34 offices had both more clinics and high repeat testing, represented by this dark blue here. And so there was a lot of opportunities to test, and people did test. However, 40% of offices that had high clinics, more than 5 across the study period, had low engagement in testing. So this represented 78 offices where there was less than 40 tests returned per clinic. So just having tests doesn't necessarily indicate, or just having clinics doesn't necessarily indicate participation in testing. However, we noticed that these light blue areas here, where there weren't that many clinics offered, but there was a lot of testing participation, 90% of those bordered a county or locality that had high participation in clinics. So these light blue areas typically bordered these dark blue areas. And this maybe indicates that people were driving across county lines to access testing. We found that repeat testing was clustered within urban areas. There was testing hotspots that are these red areas, and then repeat testing hotspots are outlined in black. And each of those areas coincided with some major metro areas, including Washington, D.C., Charlottesville, and Blacksburg, Roanoke, which is where Virginia Tech is located. We also found that 90% of participants lived within 30 minutes of an extension office. So doing those drive time analyses, we found that increased drive time was associated with decreased engagement in repeat testing. So the further you lived, the less likely you were to continue to go back for testing, which makes sense when you consider convenience. We also found that there wasn't a substantial difference between the distance that well users were driving in urban areas versus rural areas, but we found that the maximum drive time was higher for rural residents compared to urban residents. And finally, we found that repeat testing was driven by user behavior, geography, and access to resources. So the most advantaged participants, those living in urban, low poverty areas who used health-based treatment and had well system knowledge, were 2.2 times more likely to engage in repeat testing than those in the most disadvantaged areas. And so the predicted probability of repeat testing increased from 11.8% to 25% from those factors. And so just to break down this figure here, use of health-based treatment and location in urban area increased the probability of repeat testing. Living in a block group that had more poverty decreased that. And then increased testing opportunities, including staffing and clinics, increased the likelihood. And so the main takeaways were Virginia has a robust and growing participation in routine private well testing, highlighting water quality trends across the state. Repeat testing had quantifiable benefits for water quality outcomes and treatment, and participation in testing was influenced by the use of treatment and place of residence. So that was a lot. To unpack it all and try to succinctly conclude, I'm going to give takeaways that I think different stakeholders should consider. So first, for well users, I'm looking at you. Contamination can occur without visible flooding. Upgrades to sanitary wellheads significantly reduce the risk of floodwater entering your system. And repeat testing, so continuing to test over time, can improve your water quality awareness and outcomes. For practitioners, program visibility and access can increase participation, but it requires investment, time, and money. Collaborations with researchers can yield actionable tools, like what we saw in North Carolina, and rapid localized outreach is critical during disasters so that well users are informed to make decisions to protect their systems. And finally, for researchers, well contamination issues are complex and require the integration of hydrologic, behavioral, and well infrastructure data. A lot of this work required collaborations across multiple disciplines, and we still don't have the full picture. We also need to contextualize these changes in contamination with real-world data under routine conditions. So continuing sampling efforts is really important. And finally, partnering with communities is powerful to give local context and ensure that findings are actionable.